going here. Well, welcome back to our last lecture. Let me pull up the calendar so we can all see, in case you haven't had a chance to look at the calendar, where we're at. Today, obviously, is the 1st. Okay, we have coming up on Thursday, you have activity, the last activity, number 10. And yeah, we're there. Exactly. We are there. And so activity number 10, Thursday, I set homework 14 for Saturday, and then the 7th for the last homework 15. Chapter 15 is very short. We'll be done with it today. It's about 10, 12 slides, very short. Then, okay, no problem, Jason. Yeah. If you get back, I'll let you back in if you have, if you get kicked out for some reason. And then on the 8th, we have exam number 5, which covers chapters 13 through 15. And obviously, we're done with the lectures. So the 10th will be study day. I will be here on the regular scheduled time. You're also welcome to come to my 1 o'clock class. That's not a problem. And also, you're welcome to come to my Friday FCC class, which is also at from 1 to 3. So if you need more time and lecture on my SEC class on Friday, I will be doing 14 and 15. They're a little bit behind. We'll be done with that. So I'll give you a second amount of that chapter if you need it. So that means on the 15th, which is next, on the 8th, which is the exam number 5, we won't have lecture, but I will still be here. Count that as a study day. So if you have any questions, feel free to stop by and come in with some questions, and I'll be more than happy to help you out with them. Then our final, which is for all the 130 people classes, is on Tuesday, next on the 15th. And so if you're gonna do the extra credit, I had to move that on the 16th because I need to get the grades in ASAP as soon as we're done with the final. So if you want to do the extra credit, I tied that in with the final exam. It's going to be worth 10 points of extra credit, which will be given to the final exam area, that percentage from the final exam. It's a Word document. And in that Word document, you have a link that sends you to a simulation that deals with density. In that simulation, you're basically going to be looking at blocks, either a constant mass or constant volume. You're going to calculate density. A word about that particular website. Now, what's happening is throughout the world, the Flash program Flash is being retired. So some places still allow you to use it, but not for long. This density simulation does require Flash. Now, what could be happening if you're using Chrome is that it's being blocked, but you can unblock it so you can run the simulation. And the way to do that, I put instructions on there what you can do, but very quickly, if you click on the link of that Word document and it doesn't allow you, it says Flash is blocked. The one quick fix is to go, let me highlight it. If you look at the screen, there's a little icon in the upper left corner, right where the address is at. It's a little icon and of a lock. Right now, it's in the lock position. And so my Flash ability to use Flash is limited at this point. If you click on that little icon, a menu drops. Okay, you may have Flash here. In my case, I do not. Here I got camera, microphone, automatic downloads, and so forth. What you do is you click on the site settings, which opens up another page. And if you scroll down on that page is settings for Chrome. Search for Flash, which is right here. And right now it's blocked by default. Well, you have a down arrow. You can click on the down arrow and allow it. Once you do that, go back to the screen that told you it was blocked, do an F5. That's going to refresh your page, and then the simulation will begin for you. Okay? That's a quick fix. But you shouldn't have a problem. I think most of them are, it depends on your browser, but most of them should work. If not, go through those steps to allow you to run the simulation. The other thing about that extra density, as I mentioned, it deals with density. You're going to take some blocks, you're going to immerse them into a liquid. A container has liquid with a known volume to begin with. When you immerse it, in other words, you grab with the mouse, grab the block, and then immerse it into the liquid. If it floats, continue to hold on to it and completely immerse it, because you want to get the total volume that is displaced. Some blocks are just sink, you got no problem. That gives you the volume. But for the one block, some blocks that do float, grab it, immerse it completely. Do note the liquid you put in that block into has a known volume to begin with. And it could be, say, 100 milliliters of liquid. Once you totally immerse that block, the volume goes up, say 120 milliliters. You can see that reading there. Now, the amount of displaced volume is not 120 milliliters. That block did not displace 120 milliliters. What the amount that did displace is the difference between the final volume reading minus the initial volume reading. That is the volume you're going to be working with, not the total volume. Okay, that will be incorrect, and your numbers will be incorrect. And so there's multiple steps in that simulation. Just open up the file, follow the instructions, put your data directly into the file, any comments, whatever you want, into the digital file, save it. There's a little format to save it with your name and so forth. Go back into the assignment and submit that document. And then once I get it, I'll grade it, and your points will be, if you do beforehand, I may have graded it, but you won't see the points until the final exam points are put into the system. Okay. Any questions about that extra credit? No? Right. All right. Well, in that case, let us go into chapter 15 and let's talk about coffee. No, I'm just kidding. We're going to talk about solutions. A lot of this information you're familiar with already. We're just, putting names to what you probably already know. Okay. All right. So a solution. The question is, what is a solution? By definition, a solution is a solute that has been dissolved in a solvent. Okay. The solute could be any chemical that is present in the smaller amount, where the solvent is the chemical present in the larger amount. 9 times out of 10, we're dealing with aqueous solutions when we deal with a solvent, but it could be water, for example. We're using water most of the time, but it could be any solvent, any non-water, non-aqueous system. It could even be solids, and I'll explain that here in a second. Okay. Now, we know this is, again, pretty self-explanatory. When we deal with concentration, basically anything that's concentrated has a lot of solute, and a dilute solution has very little solute. Denoted here by this glass full of could be Kool-Aid, for example, different concentrations. You can see on the far left, you got a light pink color, and the far right, a very dark color. The color is directly proportional to the concentration of the solute. In fact, we use this principle quite a bit when we're trying to determine concentrations. because we can measure the amount of light passing through that solution and measure it before it goes in and when it comes out. And that gives us a reading that is obviously, as the concentration gets stronger, we get a different reading, and we can use that uh, property to measure the concentration of unknown color solutions. Yeah. All right, so weak, strong, pretty self-explanatory. Okay, well, what kind of solutions do we have? Obviously, you're familiar with this, carbonated soda. That is a solution. We have placed gas into a liquid. And so you take these CO2 pellets and shoot that carbon dioxide into your water, you get carbonated drink. Okay, that is a solution. The solute is the gas. It could be carbon dioxide. It could be any type of gas into a liquid. Or we can have a liquid in a liquid, obviously a drink, vodka and tonic. That's a solution. Vodka being in the solute and the tonic being the solvent. We could have a solid in a liquid. In other words, we could take, for example, sodium chloride and dilute it in water, where we get a salt solution. We got dissolved sodium chloride in the salt solution. That is a solution. Or we can have gas in the gas. Our air around us is a solution, is made up of a variety of different gases, mostly nitrogen and oxygen, but we have a variety of other gases up there, carbon dioxide and so forth. Solid in a solid. A lot of people don't think of this as being a solution, but it is. We have, for example, steel. Pure iron is not a very good material to build buildings with, because pure iron is very soft. And so what is done is it is mixed with carbon. And that particular solution then allows us to make steel, which gives it strength and so forth. Another example would be most of the jewelry that we wear, our rings, jewelry, and so forth. Not 100. If it's a gold jewelry, it's not 100% gold, because 100% gold is pretty soft, and so other components, other elements are placed in it to give it strength. Okay, copper, for example, is another one. Copper in itself is very soft, but the copper we utilize for piping and so forth is an alloy, or a mixture of zinc and other things, silver, to give it strength. Okay. All right. So the key component here with respect to solutions is the cardinal rule, so to speak, of dissolving things. That is, like dissolves like. Okay. We talked at length about polar compounds and nonpolar, polar and nonpolar. So what we can extend and say that polar solutes that are polar, will dissolve in polar solvents. Okay. The converse is true. Nonpolar solutes dissolve in nonpolar solvents. Like dissolves like. You cannot get, a classic example of a nonpolar and a polar mixture is Italian dressing. We all know if you use Italian dressing, you let the bottle sit, you get two layers. You have an aqueous layer and an oil layer, because we know that oil and water do not mix. Oil is the nonpolar, water is the polar. They will not mix together. Okay. So we all seen examples of pictures of uh, oil spills cause a big mess because they do not mix. Okay. Now, when we talk about liquids and we're trying to mix liquids, we use the term miscible and immiscible. Miscible meaning that two liquids will mix together because they're maybe of the same polarity. Okay. And when they do not mix, like that example there with the oil and water, we state that they are immiscible. Now, when we talk about solids and liquids, if the solid dissolves in the liquid, in the solvent, then it is classified as soluble. If it does not dissolve, then simply it is insoluble. Okay, now how we determine that depends on the solubility rules. So those rules don't go away, we still use them. Okay. And so what we have here is a table, and the question is asked, will the solute dissolve in these particular solvents? Okay. And so the solutes are written up on top across. We got HCl, hydrochloric acid. We got iodine, I2. We got PCl3, and we have CH4, okay, which are the solutes. The solvents are in the first column, which is NH3, which is ammonia, a chemical we talked about. And then we have a hydrocarbon, C12H26. Okay, we don't, that's a general formula. Okay, just telling us that it's just carbon and hydrogen. Okay, and being just carbon and hydrogen gives us a hint as to the polarity of that particular compound. Which reminds me, the activity, one of the activities, I forget which one, I think the last one, it dealt with C4H8, which was a hydrocarbon. I was really surprised that it's good. A lot of people went out and searched what the name was, and a lot of answers was butene, which is somewhat correct. Actually, C4H4 could be cyclobutane, could be butene, either 1-butene or 2-butene, and that could be either cis or trans. But my congratulations for going out to searching the name for it, but it wasn't the correct name, unfortunately. So all you can say when you have carbon and hydrogen is simply say it's a hydrocarbon. Okay. And then we got Br2, diatomic solvent, and bromine. Well, before we can decide what is soluble and what is not, we have to first define its polarity. Okay. And so we dealt with NH3 before. We went and did the Lewis dot structures. And doing the Lewis dot structures, I also pointed out that we ended up with a lone pair of electrons in the central atom, which by default just makes that compound polar. So ammonia is very polar. Okay. Now the next one, C12H26, all we have is carbon hydrogen bonds. And remember what we said, when a molecule has nothing but carbon hydrogen bonds, are we dealing with a polar bond or a non-polar bond? Anybody remember what kind of bond?
It's a non-polar.
Exactly. Very non-polar. Okay. And so that tells us we're dealing with a non-polar molecule. Now, to get this part straight, we need to refresh our memory about polar bonds and non-polar bonds, and I'll get to that here in a second. Now, the next one was Br2. Okay. Well, we have two atoms that are the same. Are we dealing with a polar bond or non-polar bond?
Also non-polar?
Also non-polar. Now, this concept of polarity, I still find that some students are having trouble with it. Okay. And what I'm going to do is give you a very general example that you can apply to anything. Okay. A bonded to A. Okay. A could be anything. And we're dealing with covalent compounds here. Now, when the atoms are the same, represented by A, when they are the same, or somebody has a question. Sure, I'll get to the C12H26 here in a minute, Nathaniel. Okay. When the atoms are the same, regardless of what they are, okay, regardless of what they are, you will always have a nonpolar bond. Okay, now you might ask, well, why? Well, remember, the polarity of the bond is dependent on the electronegativity of the elements involved. When the elements are the same, in this case denoted by AA, the electronegativity is the same for both of them, regardless of what they are. All right. And the electronegativity is the measure of the affinity of electrons being pulled onto itself. And so these electrons denoted by that hyphen, that bond between A and A, are being equally shared amongst A and A because the pull is the same. Okay? The pull is the same. Now, when we do a simple thing is just simply replace A, whichever A you want, with B, and that could be any nonmetal that you want to put up there, but they're different. Okay? A and B are no longer the same. Just the fact that they're different, the fact that they're different results in a polar bond. Okay? Because now the electronegativity of A is different than B or vice versa. Right now, we're not too concerned about which one's stronger. We just know there are two different elements. Therefore, the electronegativity is different. Therefore, we have a polar bond. The only exception, and this would answer your question, Nathaniel, is the carbon-hydrogen bond. Okay? Yes, they're different elements, and we would think that they would be a polar bond. But the electronegativity of carbon and hydrogen is the same by the negligible. And so because of that, because the electronegativity of carbon and hydrogen is the same, the carbon-hydrogen bond is treated as a non-polar bond. Okay? And so let me go up here. And write include carbon-hydrogen. Okay? And because carbon hydrogen are essentially the same with respect to electronegativity, therefore carbon hydrogen bonds are nonpolar. Therefore, that's why C12H26 is nonpolar. When you have all nonpolar bonds in a molecule, okay, all nonpolar bonds, all nonpolar bonds equal nonpolar molecule. Okay. All polar bonds equal polar molecule except when polar bonds cancel each other. Then nonpolar molecule. Okay. I think this in a nutshell gives you how to determine whether something the molecule is polar or nonpolar by virtue of the bonds. All nonpolar bonds in the molecule, nonpolar molecule. All polar bonds in general are polar molecule, except when they cancel each other out. For example, when we had a tetrahedral example where we had carbon tetrachloride, all right? We have 4 polar bonds, carbon chloride, okay? But being tetrahedral, they are in the position where they cancel each other out. For a tetrahedral, so for a molecule with polar bonds, 4 polar bonds, and they all have the same type of bond, carbon chloride here, we end up with a nonpolar molecule because they cancel each other out. If I were to change one of those chlorides to, say, a bromide, guess what? Now that the magnitude, there's three of them of one magnitude and one of them of a different magnitude. So the magnitudes don't cancel each other out. And so even though it's got a tetrahedral, the fact that three of them are the same and one of them is totally different results in a polar molecule. Okay. The other example where we had polar bonds that canceled out was carbon dioxide. Remember we did the Lewis dot structure of carbon dioxide. We note here that carbon oxygen is a polar bond. There's two of them, one going to the right, one going to the left. They cancel each other out because they're going in opposite directions, resulting in a nonpolar molecule. Okay. All right. So that right there in a nutshell kind of puts it all together to help you discern whether a molecule is polar or not. Okay. And I think the first one is the problem that I don't think people get. But if you recognize that those two atoms that are bonded are the same, regardless of what A is, they're nonpolar automatically. Okay. All right. So with that in mind, let's take a look at HCl. Okay. HCl represents AB. So what can you say automatically? Polar, nonpolar?
Polar.
Polar, exactly. Okay. Polar species. IQ, iodine. That represents AA. Okay. Automatically nonpolar. Okay. PCl3, analogous to ammonia, NH3, phosphorus and nitrogen are both in the same group. And guess what? They end up with a lone pair on that central atom. And remember I said, anytime you end up with a lone pair in that central atom, just automatically it's a polar species. Okay. And you might think, well, wait a minute, I got three chlorides. Wouldn't they be trigonal planar and that way they cancel each other out? Well, not really, because you're forgetting that that phosphorus has that lone pair. And those lone pair cause those other bonds to bend downwards because those lone pairs take up more space. And so they no longer now are in the same plane. They're tilted downwards, resulting in a polar compound. Okay. Just like ammonia, NH3. And then we had the carbon hydrogen, CH4, which is methane, but it's again, nothing but carbon and hydrogen there. So therefore, because that represents AA, therefore we have a non-polar solute. Okay. Let me clear this up a little bit. Let me ask you a question. With respect to IMF, okay, what IMF would be involved with hydrochloric acid, HCl? Remember IMF?
Can you say that one-
Intermolecular, pardon me?
Can you say that one more time?
Yeah, IMF, intermolecular forces. Remember the last chapter we just did?
So if it's a polar force, I would like to say it's a dipole-dipole.
Okay. I mean, that's a good thing to say because that's correct. Okay, remember IMF forces, there's four of them. All right. All right. One of them was called ion dipole. The ion dipole dealt with an ion like sodium, any of the ionic compounds. Okay. There's nothing here that deals with the ion. There's no ions in here, no ionic compounds here. So we can eliminate that force. So then we have three left. We had the London dispersion forces, the dipole forces, and then we had the hydrogen bridging force. Okay. And so we look at HCl. HCl, it's polar. We all agree on that. All right. Which IMF force do we have to deal with? Well, could it be London forces? It can't be London forces, right? Because remember, only nonpolar molecules have London forces, and that's it. So every nonpolar that we have defined here, the only force that they have to deal with is London forces. And so iodine, it would be the London dispersion forces, okay? And methane. Let me get this up there. London dispersion forces. That's force. I meant to say LDF, not LDA. And it won't let me change it. Okay, London dispersion forces. And that is true also for the C12H26. Okay. And guess what? The bromine too, right? Those are the only forces involved for those particular molecules. Now, what about HCl? Well, it's not London force. So the only thing left is dipole and London bridging, or excuse me, London bridging, hydrogen bridging. Let me wake up here. Hydrogen bridging. Okay, well, let's find out about hydrogen bridging. Well, we got hydrogen here, so maybe it's hydrogen bridging. But remember, not on file, NOF, that only dealt with hydrogens that were bonded to nitrogen, oxygen, and fluorine, which is not the case here. It's chloride. And so the only force involved for HCl is dipole. Okay. And by process of elimination, looking at PCl3, again, obviously not London forces because it's polar. And it's not hydrogen bridging forces because there's no hydrogen involved here. It's phosphorus and chloride. So the only force that's involved with PCl3 is dipole. Okay. What about ammonia, NH3? What do you think? What force can I assign to ammonia?
Dipole.
Mm,
Oh, no, it's the hydrogen bridging because
got it.
it's connected with the nitrogen and a hydrogen.
Got it. Exactly. Okay. Because yes, at first, yes, it has a dipole because we got a polar bond. However, because we got hydrogen bonded to nitrogen, then that supersedes the dipole interaction, and the hydrogen bridging is the stronger force. Okay, so now you've defined the IMF interactions for all of these guys. And if you look at the solutes, if you were asked, of those four solutes, which two solutes would have the lowest boiling point? What would you say?
The ones with the London force?
Yeah, okay, because remember, now go back, you look at the three forces and the strength. The weakest was the London dispersion forces. The strongest was the hydrogen bridging forces. And the dipole was somewhere in the middle of the two. And so that means the one with the weakest forces would hold on to the other molecules much less, with less strength. Therefore, they would easily have a lower boiling point. So all the ones with the LDF will have a lower boiling point than the others. We can't give it a specific number. All we can do is do a relative comparison. Okay. We can't even give it for the size of LDF between iodine and CH4, all we can say they're both low because they're both about the same size. Okay. All right. All right. So with that being said, these are the type of questions that could come up that, how you say how we built up on it. We built up on how we had to figure out the polarity of the bond, from there, the polarity of the molecule, and from that gives us the IMF interaction. And from that, we can do some relative comparison of boiling point, even vapor pressure, surface tension, and so forth. Okay. But back to the original question is who's going to dissolve in, which of the solids dissolve in these solvents. Keep it in mind, like dissolves like, okay? Like dissolves like. And so we got a polar ammonia with a polar HCl. Yes, they're going to dissolve, okay? Yes, all we can say, yes, they're going to dissolve. Yes, there's a magnitude of something dissolving. There's a limit, but all we can say is yes, they will be soluble. Okay. The next one, ammonia and iodine. No, it would precipitate because iodine is very nonpolar and ammonia is polar. The PCl3 more likely will dissolve because both of them are polar. Okay. And the second one with not the second one, the ammonia, not ammonia, ammonia and CH4. The answer.
Dr. Fred, I have a question.
Sure, go ahead.
So for when we see these type of questions, we can also use the solubility rules when answering these.
If you look at the solubility rules, we're only dealing with water and ionic compounds.
Okay.
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 Hey, you got the solubility rules there in front of you.
Yes, sir.
Okay. Look at them. All of them are ionic compounds. Okay. So the solubility rules will not play a factor here when we're dealing with non-ionic. Everybody here is a covalent compound. And so
Okay.
you see, everybody here is covalent. There's no ionic compound in here at all. So the solubility rules wouldn't be a factor. Plus, we're not using water. We could put water in here, but then we would not use the solubility rules. We will use the fact of polar versus polar. And the like dissolves like.
Okay.
Okay.
Just wanted to ask. Thank you.
No problem. Good question. Then we had the C12H26, big old hydrocarbon. And we get no, because we got hydrochloric acid, which is polar. Okay. We get, again, the hydrocarbon with the iodine. And we get a yes. Yes, it's soluble because both of them are nonpolar, like dissolves like. The next option, no, because PCl3 is polar and C12 is nonpolar. That C12 that could be like a vegetable oil, pretty big. It's very nonpolar. Then we have yes for methane and the big old hydrocarbon. Okay. And we continue with no for bromine and hydrochloric acid, again, because of the polarity of the molecules. Yes for bromine and iodine, because both of them are nonpolar. And a no for PCl3 and bromine, because of difference in polarity. And then yes for the final one. Okay. So in this example, a good way to maybe remember this, and I use this quite a bit as an example, and you ladies out there, correct me if I'm wrong, but there is, what do you use to remove your makeup at the end of the day? Do you use soap and water? or do you use an oil-based cleanser?
I use soap and water.
Soap and water, okay. What does that infer about the makeup that you're using if soap and water takes it off? That the makeup has a lot more polar properties to allow it to dissolve. Plus the soap also helps in there. But there are some makeup, I'm told, and I use this analogy a lot. They call it hurricane proof makeup, that water just won't wash it off. You used to use like a 1040 weight oil, take it off or something because you're dealing with a very non-polar makeup. Okay. So non-polar makeup requires non-polar cleanser. And yes, the soap does have non-polar properties, but if you were to use a non-polar, totally non-polar cleanser, you'll find that stuff come off quite a little bit easier. Anyway, let me clear the drawing here. All right, so again, like dissolves like. When we're dealing with miscible, immiscible, soluble, insoluble, this is pretty self-explanatory. I'll go through it very quickly. Remember, when we deal with the term miscible, we're dealing with two liquids. Miscible and immiscible deal with liquid and liquid. Soluble, insoluble deal with solid and liquid. And so if we have a polar liquid and a polar solvent, both liquids, then because they're polar, they're going to dissolve in each other and therefore are classified as miscible. If one of them is nonpolar, they are immiscible, two liquids. Nonpolar liquid, polar solvent, immiscible. Nonpolar liquid, nonpolar solvent, they're miscible. Okay. A solid, polar solid, and a polar solvent will be soluble, whereas a polar solid and a nonpolar solvent would be insoluble. Nonpolar solid, insoluble in a polar solvent, and soluble in a nonpolar solvent. Now, when we get to ionic solids, now, and you got a polar solvent, what we got to look at is solubility rules. Okay. When we're dealing with an ionic compound, now remember the definition of ionic compound: metal, non-metal. All right. Now, with respect to ionic solid and a nonpolar solvent, it would be insoluble. Bear in mind, if you put a little, you're cooking something, you got some hot water in your pan, you throw some salt, hey, the salt dissolves. Take some oil, put it in a pan, heat it up, throw some sodium salt in there. Your salt will not dissolve because the oil is nonpolar and you have this salt, which is an ionic compound. Okay. All right. We did have a picture of this before, but basically the solvating is simply the water molecules. When we're dealing with an aqueous system, water is very special. It's two dipoles. We have a very strong partial negative side. And so the oxygen solvates the sodium ion. And then the other end on the protons, the chloride ion, if this was a chloride, would be solvating that side. So water is very strong. It's very good about dissolving things. Most everything will dissolve eventually, even things that are placed in water, eventually it'll go in solution. Some take very quick, but some take years. All right. With respect to concentration, we're going to be using two types of definitions of concentration. We have what is called the mass percent, and that's simply the weight over weight percentage. Okay. And then we're going to deal with molarity. Molarity was introduced a little bit when we did the chapter on pH, where we took the molarity of the hydrogen ion concentration, which was defined as moles per liter. Okay, here's the moles again. All right, so what we need to do is, one, When we need to calculate the moles of something, we're going to need molar mass because we're going to divide the grams of whatever we're looking for by the molar mass. So refresh your memory on the molar mass. We have some examples here. And then we take that number and divide it by the volume in liters, okay? So sometimes the question could be given to you in milliliters. You need to convert that to liters. Remember that in 1 liter, there are 1,000 milliliters, okay? So let's take, for example, an example of a mass percent, okay? They want you to calculate the mass percent if you take 15 grams of potassium nitrate and we dissolve it in 135 grams of water, okay? By definition, we take the mass of the solute, which is 15 grams, and we divide it by the mass of the solution. That means the weight of the solute plus the weight, in this case, the water, okay? And so that's the sum. So we got 15 divided by 15 plus 135 times 100. So this particular solution consists of 10% by mass. You have other examples. You have mass over volume. You have volume over volume. A lot of the wines out there to give you a percentage. It's normally volume over volume as far as alcohol content. Some of them give you mass over volume, but we're just going to deal with mass over mass. Now, occasionally, they will give you an example, a problem where you need to calculate how much water you need to use if you need to make a certain percentage of a solution starting with a certain amount of salt. In this example, they want you to calculate how much water you need in weight to make a 5% solution that has 10 grams of a salt, which reminds me here, when we deal with mass percent, there's no concern about the molar mass. Notice that we use potassium nitrate. We had nothing to do with molar mass here to calculate the moles or anything, just simply the weight of that material, okay? And that's why they put in general terms 10 grams of a salt. They could be anything. And so we set this up. We know we need 10 grams. They're given 10 grams of salt. And so we got 10 divided by 10 plus X. X represents the quantity, the weight of water, okay? And then we plug in the rest, where we got 5% is equal to 10 divided by 10 plus X times 100. Okay, so we need to solve for X. Now we're going to use a little bit of algebra, nothing complicated, okay? And sometimes in algebra, you can solve for X problems any multiple ways. This is just one way. Okay, so well, we got to isolate X because that's what we need to find out what it is. So one way of doing that is to multiply both sides of the equation by 10 plus X. If I multiply 10 plus X on the right side and the left side, I cancel the 10 plus X in the denominator on the right side, okay? Bringing the 10 plus X quantity to the left, all right? Now, at this point, you can go any multiple ways. And what they do here is if they went ahead and multiply 100 times 10, which is 1,000, okay? And again, you can do this in multiple ways. You can multiply 5 times 10, 5 times X, and then work it that way. Or you can divide everything by 5 to isolate the 10 plus X to give you this. So if I divide everything by 5, both left and right side, now I have the quantity 10 plus X isolated and 1,000 divided by 5, okay? Carry that math out, that's 200. So now I have the quantity 10 plus X equals 200. Now I really simplify the equation. Now I need to isolate X, which means I need to subtract 10 from the left side and 10 from the right side, and X is 190 grams. Now I write it in scientific notation as 1.9 times 10 to the second. Why would I write it in scientific notation here? Any reason I wrote it as 1.90 times 10 to the second power and not just give the answer as 190 grams? Remember what we did way back in the beginning, first couple of chapters, we dealt with what? Sig figs, right? And significant figures, because I'm going to have 3 sig figs. My answer should have 3 sig figs at the end. And if I write it as 190, I only have 2 sig figs. So whenever you want to write any number with the correct number of sig figs, you put it in scientific notation, because we know that 1.90, those are 3 sig figs. Okay. Double check your answer. How do you do that? Well, take the 190, plug it back into X, and do the math. And you should end up with 5.00 on both sides of the equation. And that means that you solve for X correctly. So this means that if I take 10 grams of ACE salt and 190 grams of, in this case, water, I make a 5% solution. Okay, 5% solution. Did anybody ever have to do have a IV solution used on you or someone you know? They probably need a saline solution. That is a 0.9% sodium chloride solution. And you can calculate how to make one now. Okay, here you can make one in emergency. All right, now let's go deal with molarity. Molarity by definition is moles of solute divided by the liters of the solution, okay? Whereas we had mass percent, we divided by the weight of the solution. That incorporated the weight of the solute and the weight of the solution. Here, it doesn't do that. It's just the volume of the solution. Okay. So we're asked to calculate the molarity of potassium bromide. If we dissolve 9.9 grams of potassium bromide and we dissolve it in 2.50 liters of solution, okay? So now we're given grams of potassium bromide. So we need to calculate the moles. Well, we need to write the formula, the correct formula. So here we go again, we're writing formulas, okay? So when you write the formula, as I've preached in the past, write the ions first so that you can make sure that when you put them together with the correct ratio. All right, so potassium bromide. What is the symbol for potassium? Let's start with that.
It's a K.
K, all right? Uppercase K. Now, for ionic potassium, what would be the charge for ionic potassium?
K plus.
I didn't hear what you said.
K plus.
Oh, a plus? Okay, that is correct. How did you come up with plus?
I kind of just knew that. It was like
Okay, well, that's an honest answer, but let's just say you didn't know that, okay? That's an honest answer. All right, so you find potassium, refresh your memory here, okay? We got to find ions. Remember, the elements on the periodic table are not ions, but their position tells us how many valence electrons they have. So if you look up potassium on the periodic table, look for K, you'll find it to be number 19, and it is in group 1. Group 1A tells you that there's 1 valence electron. So that's point number 1. Point number 2, potassium is a metal. And remember what I said about metals? Do they gain or lose electrons? They lose electrons. All metals lose electrons. Now, everybody's trying to fulfill the octet. Now, when you got potassium with 1 valence electron, 1 electron, it's got 19 electrons, right? But one of them is in the outermost shell, the valence shell. Is it easier to want to pick up 7, remember the octet, or to get rid of 1? But yeah, it's good easier to get rid of 1 than try to put 7 back in. Too much energy involved there. So it's going to give up that 1 electron to give you the next layer in, which is full, which is the octet. Now it's full. And by losing 1 electron, now it started off with 19 electrons, now it has 18 electrons. It still has 19 protons, but now has a net charge of +1 because there's 19 pluses and 18 negatives. That's a net of +1. Okay. Now, what about the other guy? It says bromide. So we're dealing with an ion. So what's the symbol for bromide? Okay. Anybody know?
BR.
BR, exactly. All right, now we got to figure out the charge for bromide. Okay, find it on the product table. It's in group 7. Okay, so that's point number 1. Point number 2, it is a non-metal, and counter to the metals that want to gain electron, non-metal, counter to metals that want to lose electrons, non-metals gain electrons. And they're going to gain 1 because it's in group 7. It's got 7 valence electrons. It's going to pick up 1 very easily. So 1 electron ends up with a -1. And so here we can very quickly put them together to write the formula, because we need the formula to figure out the molar mass so we can figure out how many moles we have. And so since potassium is +1, bromide is -1, the formula is simply 1-to-1, which is KBr. Okay. We look up the atomic weight for bromide, look up the atomic weight for potassium. You should end up with 119.00 grams per mole. Okay. And I write the molar mass with moles in the numerator and grams in the denominator, because when I do the math here, I want to make sure that grams cancel, leaving me with moles of potassium bromide. And do the math, I end up with 0.08395. I carry all the digits, don't truncate anything until you're done. Okay? Because you're dividing by 3 sig figs of 9.99. In the numerator, and then you're going to divide by 2.50, which is 3 sig figs. So your answer should have 3 sig figs. So don't truncate anything until the very end. So take that number of moles divided by 2.50. Now you have an answer of 0.0336 moles per liter. All right. That is the molarity of potassium bromide if I take 9.99 grams and I weigh that out and I dissolve it up to 2.5 liters. That is my concentration. There are some more examples in the textbook and the practice worksheets. So, do some more of these to calculate the molarity and so forth, and the mass percent. Let's do one more. This says calculate M, capital M, which is molarity, which is defined moles per liter, if 5.0 grams of sodium phosphate is dissolved in water to make 255 milliliters of solution. Okay. Well, first things first, I need to figure out the formula. All right, so let's write everything in ionic form first to make sure that we put it all together. And sodium is Na. Okay, what about the charge of sodium? What would that be?
+1 charge.
+1 charge. Same reasoning as the potassium. It's in group 1, 1 valence electron. It's a metal. It will lose that 1 valence electron with resulting in a +1 charge. A little bit more challenging is the phosphate. Okay, phosphate should tell you I need to go to the polyatomic ion table. Okay, because it's not phosphorus, it's not phosphide. If it was phosphide, it would be simply E by itself, but it's ATE. That's a good flag. ATE and ITE is a good flag for you to go to the polyatomic ion to figure out the formula for this. Same is true with nitrate, nitrite, sulfate, sulfite. Okay. If it is just an IDE phosphide, then it's just simply the single element itself. Okay, but we're dealing with phosphate. And if you go to the polyatomic ion table, you find the structure given there. This PO4 with a -3 charge, polyatomic ion. Okay, well, now that I got them in ionic form, now I can put them together with the correct formula. And since sodium has a +1, I need 3. Remember, I got to put them together so that the positive and the negatives cancel each other out. Okay. So I need 3 sodiums for each phosphate. So that 3 becomes the subscript for the formula. Now I know Na3PO4. I know how many sodium I need, how many, I got 1 phosphorus and 4 oxygens. Okay, going to the periodic table, getting the atomic weight for each one, I end up with a total atomic weight of 163.94 grams. Okay. And I have 5.0 grams of sodium phosphate. There's a formula we just went through. Its molar mass is 163. I'm dividing by 163.94. That gives me 0.0304, et cetera, leaving all the digits there until you're done. Now I'm dividing this by the volume, which is 255 milliliters. Remember, molarity is moles per liter, so I need to convert the milliliters to liters. And I use this conversion factor where I divide the milliliters by 1,000 to give me the number of liters. Okay. So that's 0.255 liters. So now I just do the math. And I end up with 0.12 moles per liter. That is the molarity of a sodium of 5 grams of sodium phosphate that are dissolved to give me a final solution of 255 milliliters or 0.255 liters. That's its concentration. All right, with that being said, don't forget the assignments we talked about, okay, that are coming up. There is a practice final exam on the website, so you may want to look at that. Other than that, ladies and gentlemen, congratulations, you finished 15 chapters of chemistry. And so it's been a pleasure, been challenging, but that's okay. We're learning. Get an evaluation set up, uploaded, so I can get some feedback. I'll see if I can get something up there because I could always use feedback. There's always room for improvement. This online thing can be very challenging. I realize from your end, also from our end, trying to present information online is a little bit different, a lot different than being in person. Okay, any questions? You know what?
There is